Yeah, so thank you, Gary, and thank you all for the invitation to join you all virtually. One side effect of these virtual meetings is it allows those of us to interact from longer distances than perhaps we would have before the pandemic. This evening, I'm going to talk about soil carbon in natural and restored lands. But before I dive into the heart of that talk, I want to take a moment to say thank you to several of the people who helped me in my role and support my work here at Nachusa Grasslands and more broadly within the Nature Conservancy in Illinois. My colleagues here at Nachusa are Bill Kleiman, Cody Constine, and Dee Hudson. I also want to give a special shout out to Dee Hudson and Charles Larry. You're going to see several of their beautiful photographs throughout this presentation, and they deserve more credit than I can give for their fantastic photography skills. And of course, the Nature Conservancy for supporting my role as a scientist and the work I do, such as sharing with groups like yours. So how many of you are intimidated by the topic of carbon sequestration? If we were in person, I'd ask you to raise your hands. Since we have the videos off, I'm going to assume some of you probably are a little intimidated by this topic. I'll be honest, I'm intimidated by it, and I'm the one who's supposed to be talking about it. So I'm going to invite you all to take a big, deep breath with me so we can settle in and learn more about this. Okay, well, at least I'm feeling a little bit calmer. The atmosphere is actually a pretty good place to start a conversation about carbon cycling and natural areas. Our atmosphere, 99.9% of our atmosphere is made up of 3 gases. Again, if we were in person, I'd ask you all to guess what these gases are. And maybe some of you know chat well enough, you want to put some potential answers in that chat. Let me pull that up and look at that. All right, so any guesses on what the 3 primary gases in our atmosphere are? All right, I see a nitrogen, oxygen, hydrogen, nitrogen, oxygen. All right, we got an argon on the board, nitrogen, oxygen, CO2. All right, really good answers, everybody. This is a well-informed group. The answers are nitrogen, 78% of our atmosphere is nitrogen, oxygen, 21% of our atmosphere is oxygen, and argon, just under 1% of our atmosphere is made up of argon. So many of you guessed carbon dioxide, and that's a really good guess because we talk about it a lot. Carbon dioxide is, the current concentration is just over 400 parts per million. That's about 0.04% of our total atmosphere. So if it's such a tiny amount of our total atmosphere, why are we so obsessed with it? Well, some of you may have taken a chemistry class back in the day, and maybe some of you thought, I'm never going to need this in real life. Well, today's that day in real life where we're going to use a little bit of basic chemistry. The thing that nitrogen, oxygen, and argon all have in common is that they're incredibly stable molecules. In our atmosphere, nitrogen exists as N2, and several of you in the chat noted that directly. It's 2 nitrogen atoms, and it's a triple bond. They're sharing 3 electrons. That means this is a very tight bond, and it takes a lot of energy to break that bond. It's really hard to do. So this gas behaves fairly inertly in our atmosphere. It doesn't really react with much of anything. The exception is in like a lightning storm. You can actually break some nitrogen bonds through an electrical charge. Oxygen is slightly more reactive, but again, in our atmosphere, it's present as O2, a double bond, and that's a very stable bond, especially when in mixture with nitrogen. And we can kind of think about these double and triple bonds as putting a pair of elastic bands around our hands. If we put 1 pair of elastic band, we can kind of stretch it. 2, it gets a lot harder. 3, it's almost impossible. It's a similar process here. These bonds are very tight. These molecules are very stable. And argon is one of those things that we call a noble gas or an inert gas. Its outer electron shell is full of electrons. It doesn't like to react with anything. It's a very stable, non-reactive gas in the atmosphere. So 99.9% of our atmosphere is made up of gases that just aren't reacting with much of anything. Carbon dioxide is a little bit different though. In carbon dioxide, we have a central carbon molecule and two oxygens, and there's two bonds connecting that carbon to that oxygen. And what these two bonds means is that there's a little bit of flexibility in that movement. Let me see if I can play that again for you all. So what happens in the atmosphere is sunlight is hitting those electrons and exciting them, and that causes those bonds to stretch out a little bit. And then those electrons are going to collapse back down into their normal orbitals, and that releases heat. So the sunlight excites them, heat is what comes out when they relax. And that wibble wobble is actually what's generating heat in the atmosphere and why we call carbon dioxide a greenhouse gas. And in fact, the other greenhouse gases like methane or nitrous oxide is the exact same principle. There's just more bonds in those molecules, and they're able to wibble wobble and release heat in a way that those inert gases are not. But you all invited me here to talk about native ecosystems and soil carbon. Why am I talking about atmospheric gases? So let's all take another deep breath and refocus. All right. What did we just happen when we breathed in? When we breathe in, we as people, we use the oxygen. And oxygen reacts with the dinner or snack that we just ate, breaks it apart. It can produce the mass that becomes our bodies, our muscles, our organs, our bones. And it also produces the heat that keeps us warm on a cold night like it is here in Illinois. So oxygen in, CO2 out. That's a basic combustion reaction, and it's how all warm-blooded organisms function. Wouldn't it be great if we could reverse engineer that and just take in CO2, turn it into solid parts, and release oxygen at the end? Right, plants already do this through photosynthesis. And this group probably already knows this, but it's using sunlight to directly take up carbon dioxide specifically from the atmosphere and to produce roots, leaves, stems, flowers, fruits, the whole 9 yards. And the byproduct of that reaction is oxygen. It's the complete reverse of our normal metabolic combustion. Bonus points, plants are 100% solar powered, and they've evolved to maximize carbon dioxide uptake in ecosystems all around the world. So we just need more plants, right? That'll take care of our excess CO2 in the atmosphere. Well, that is true to an extent. And if there's only one thing you take away from this talk tonight, I hope it's that, more plants. But of course, plants aren't just a uniform thing. There are more than 390,000 species of vascular plants on Earth. Over 2,000 new plant species are described every single year. We're learning more every year about the type of plants and the diversity of plants on Earth. 21% of plants worldwide are actually threatened with extinction. We're actually losing the ability to take up CO2 through plants in numerous habitats around the world. And of course, some plants can cause negative consequences. About 5,000 plant species worldwide are considered invasive, where they may be taking up a lot of CO2, but they're threatening other important ecosystem services like biodiversity or water quality. So to add one more condition to this, more plants in the right place. It's important for us to pay attention to where plants are in where they're native in their range, where plants have evolved and where they're going to thrive into the future. But you invited me here tonight to talk about soil. You all probably know a lot about plants already. So let's take one more breath and dive into soil. Did you know that soil breathes too? Snoopy, ever a beacon of wisdom, is going to help walk us through this. So we see in the comic here, Snoopy's watching a leaf fall off of a tree, probably this time of the year in autumn. And in the final pane, the thought bubble says, "You don't know it, leaf, but your troubles are just beginning." And sure enough, Snoopy's hit on the heart of the process between atmospheric carbon, plants, and soil, and that's decomposition. Soil organisms like earthworms, fungi, springtails, bacteria, and nematodes all digest dead plant material for lunch, just like we might enjoy a delicious salad. When they digest these plants, they're eating that tissue and they're using it to build body mass, sometimes to produce heat. And again, they're respiring carbon dioxide as a result of that. It's the exact same process that we just did when we took a big breath of air and helped process the food we've eaten earlier today. However, it's really hard to measure respiration on any of these single organisms, particularly these microscopic single-celled organisms. So we often like to basically measure respiration for soil as a whole. We put a little collar in the soil, we put a lid on it, and we can actually measure the gases coming out of the soil, including carbon dioxide, including oxygen, including other gases. And what we can realize is that this decomposition process can produce CO2, just like photosynthesis pulls it out of the atmosphere. And an important thing to know about our Earth is that our land mass is disproportionately allocated into the northern hemisphere. There's just a lot more land in the northern hemisphere than in the southern hemisphere. So when the northern hemisphere, especially the temperate zones, are in their growing season, where lots of plants are growing and photosynthesizing, it's taking up a lot of CO2 in the atmosphere. And we get a picture of our atmospheric carbon dioxide concentrations that looks like this. The bluer colors are a lower concentration, the bright red colors are a higher concentration. However, if we fast forward to December, when the northern hemisphere isn't photosynthesizing, we see a strong increase in that concentration of CO2 in the atmosphere. And this can kind of be thought of the Earth's exhale process. And if we watch this as a video, starting in January, we can begin to see these swirls of red, that CO2 concentration increasing, and that slowly accumulates up in the northern hemisphere. This can be considered Earth's exhale process. They're exhaling CO2. And some of this is coming from natural decomposition. Some of this is coming from burning fossil fuels. You'll see that the swirls of red are coming from densely urban areas. And that is largely fossil fuel carbon dioxide production. You'll notice the southern hemisphere doesn't have the same elevating concentrations. It's because it's photosynthesizing in the southern hemisphere. And you may also notice the Amazon rainforest and the rainforests over here in Indonesia and the South Pacific kind of doing this almost heartbeat look. And those are what we sometimes call the lungs of the world. Those are those tropical rainforests. They're photosynthesizing all year long, and they're just pulling in CO2, releasing CO2 through decomposition, and there's a balance. It's largely balanced there. Now, to return to our global story, as we start looking at the northern hemisphere, we've reached June, and you're seeing the red quickly dissipate out of the picture. That's because the northern hemisphere has reached maximum growing season, and the plants are taking up a lot of carbon dioxide. And we'll see this continue on through July and into the end of the growing season. Now, in kind of natural status quo situations in Earth, the CO2 taken up by plants and the CO2 released by decomposition is largely in balance. And in fact, it's actually shifted towards taking up more CO2 than is released through decomposition, because we have plants like trees that produce mass that stands for a long, long time, and because of soil. And some of this, so when we think about carbon in our world, it lives in several different places. The biggest pool of carbon on Earth is in rocks. This includes things like limestone or coal or oil. The second largest pool of carbon on Earth is the ocean. There's a lot of carbon dissolved in the ocean. And in fact, the ocean can be really good at buffering atmospheric CO2 because that atmospheric carbon dioxide can dissolve into the ocean water. Now, a drawback to this is that when CO2 dissolves into ocean water, it produces carbonic acid, and that can lead to ocean acidification, which can have some negative consequences for marine life. Soil is the third largest pool of carbon on Earth. And this is carbon that, again, gets stuck through the decomposition process. It's generally very stable for decades or sometimes even centuries. And it doesn't really have any negative consequences to having a lot of organic matter in your soil. So it's considered a very low risk approach to thinking about where we can put carbon. We also have the ability to add carbon to soils in a way that it's much more difficult to do for rocks. And then the fourth largest pool is the atmosphere. And I put this on here just so you could see the scale of difference in carbon in these pools. The rock pool of carbon is just orders of magnitude larger than any of these other pools. And in fact, when we're burning fossil fuels, we're taking carbon from the rock pool and putting it into the atmospheric pool. And that's one of the only routes from rock carbon to atmosphere or air carbon. Most of the carbon cycling that's happening biologically is between plants, animals, soil, in the atmosphere. And those are all very tiny pools. They don't even show up on this list. And those are not really what's contributing to changing climate. What's changing climate is the change from this rock pool to the atmosphere. So when we want to think about putting carbon into soil, decomposition is really the route we're going to take. And there's several factors that limit decomposition. One is temperature. Warmer temperatures, decomposition happens faster. You usually get more respiration. Oxygen availability, just like we need oxygen to digest our food, soil organisms need oxygen to digest their food. So in a soil matrix where oxygen may not permeate very far, that can limit decomposition. Access to that plant material. So again, in a soil environment where that can all get enmeshed, it can limit the access to that plant litter. Fire, a wildfire that combusts a lot of above ground plant material sends that out as greenhouse gases versus low intensity fires that are often more historical in grasslands and even forested systems, and often set by indigenous peoples. They don't actually negatively impact long-term above ground carbon in trees. It's surface carbon that's going to decompose in the next year or two anyway. And then of course, human activity, how we choose to manage our land and the ways we choose to build our lifestyles. So to get to the root of the issue, one of the key ways to get carbon below ground into the soil is through plant roots and plant exudates. A lot of the above ground plant material is going to die back at the end of a growing season and decompose, like the leaves in my backyard. Roots, however, are underground. They're protected from that surface decomposition because oxygen isn't very available, and sometimes water is limiting as well. That root carbon is really what's driving the accrual of soil carbon. So roots are really important. They also play a really big role in helping to enmesh this organic matter into soil. So it makes it harder for microbes and other organisms to decompose it. And that's really how soil carbon gets stuck for decades to centuries. So to build on our story tonight, we want to look at more plants in the right place with less decomposition. That's how we're going to build soil carbon. That's how we're going to save the world, right? Well, let's take another deep breath because there's a few more caveats we need to talk about. Soils have a carbon saturation point. Similar to a glass of water, like this one, soils can hold only so much carbon. And once this glass is full of water, or once that soil reaches that carbon storage point, it just overflows and it reaches its balance. It can't hold anymore. So in a soil, this means that respiration usually increases and that pool of carbon stays more or less stable. If we add more carbon, it's just more respiration. So we need to be thoughtful about what these saturation points are and how we use them when we're thinking about managing soil carbon. So I did bring some data to share with you all tonight. These are 3 graphs from 3 different papers. On the far left, well, I guess for all of these graphs, on the y-axis, you're looking at a measure of soil carbon. On the x-axis, you're looking at time since restoration. These are all examples from tallgrass prairie restoration projects. And in the middle 2 graphs, or the 2 graphs on the left, on the far side of those graphs, you're seeing some native prairie remnant habitat for comparison. These are remnants that have never been plowed, native prairies. So on the far left, we're looking at a figure of soil carbon done at a prairie restoration in Illinois, about 80 miles east of where I'm sitting tonight, on a fairly clay-rich soil. These restorations, you can see, do have an increase in soil carbon over the time that it was measured. And these authors have modeled out the expected increase in soil carbon to reach remnant levels. In the middle graph, we're looking at soils from Nebraska. Again, technically tallgrass prairie ecosystem, but much less moisture and less plant productivity. And on the far right side, we're actually looking at some data from Nachusa Grasslands, where again, we're looking at soil carbon over time with restoration. And we can see in all 3 of these examples, soil carbon is increasing with time since restoration started. What I want to point out is that actually the scale on all 3 of these y-axes is not the same. So I've added a gold star to show you the exact same absolute value of soil carbon on each of these graphs. And what you can see is that the soil from the clay-rich Illinois soil here on the left has more carbon. That gold star is at a lower point on the axis. Whereas the Nebraska soil and the Nachusa soils, which are much sandier, I might add, than these other 2 soils, we see actually are holding less carbon, even in the prairie remnants. And this is an example of that carbon saturation point. All of these soils can hold carbon, but a clay-rich soil in an area with high plant productivity, because there's a lot of moisture, it's able to hold more carbon. And in fact, in these examples, the clay-rich soil is holding about 3 times as much carbon as the drier Nebraska soils or the sandier Nachusa soils. And this is the difference between your 8-ounce coffee cup and your 32-ounce big gulp. And when we break down the rate at which these soils are accruing or pulling down carbon, we actually see that those rates are fairly similar in the left and the right 2 graphs, and a little bit faster in the left graph. But because there's such a big difference between the restoration and starting point and the remnant habitat in this far left graph, it takes twice as long, almost 300 years, to reach those remnant prairie carbon levels. So there's 3 steps to soil carbon management. There's accrual, and that's what we were looking at with those restorations. That's the ability for a soil to gain carbon through impartial decomposition. That's the process of filling up those glasses. Storage is the second step, and that's the ability for soils to hold carbon for a long period of time. And that's essentially kind of getting at the soil saturation point. Once carbon's in the soil, does it stick around? And then the final kind of component is really what we call sequestration. And generally, when we're talking amongst people, we'll use the word sequestration pretty liberally, but it has a very specific scientific definition. And in the scientific world, for it to truly be carbon sequestration, there has to be some confidence that that carbon is going to stick around in that pool, in this case, soil, somewhat indefinitely, or at least for many centuries. And this is a really hard thing to know for sure. We can spend a lot of time in the scientific world trying to estimate and understand that, But at the end of the day, we don't really have time to sit here and watch a soil for 300 years and figure out how effective it really is at truly sequestering. So this is one of the biggest unknowns when we're talking about soil carbon, is our confidence that that carbon will actually stay in the soil, even if the temperature gets warmer and decomposition rates accelerate, or if moisture regimes change and that shifts carbon respiration. All of those factors make it really difficult to guarantee with any confidence the long-term ability of these soils to hold on to any carbon we might add to it. But I don't want to bum you out. I do have some really helpful action items that really can make a difference in our world. And I like to break those down into protect what we have and restore where practical. So to protect what we have, I found this Far Side comic to really embody this ethos. We have here two men who've just sawed down a large tree, and the older gentleman is saying, and you see this ring right here, Jimmy? That's another time when this old fella miraculously survived some big forest fire. So what we have here is a tree that's withstood natural disturbances probably for centuries, and a pair of humans have come by and cut it down and are marveling at its lifetime. Where I live in Illinois, we don't have a lot of native habitat left. In the 1850s, this landscape was dominated by tallgrass prairie and riparian forests. Today, our landscape is dominated by row crop agriculture in some dense urban areas, particularly in the greater Chicago region. And while this transformation has certainly optimized the ecosystem service of producing grain, it's caused some other consequences that are a concern. The little bit of native habitat that we do have left in Illinois is really important to hold on to. And to break down this example, I'm going to share some data from some colleagues of mine at the Nature Conservancy. Now, keep in mind, this analysis was done at a global scale, so it doesn't necessarily scale down to Illinois or to Texas or to any of our individual communities in exactly the same way. But the point I want to make is that when we look at these green bars, which are the potential for climate mitigation, we see that avoided grassland conservation is actually one of the bigger opportunities we have to address climate change through greenhouse gas mitigation. And this is, again, a global estimate, so it includes a lot of grasslands around the world that are more or less intact. Particularly here in Illinois, we just don't have very much of intact. But you can see how protecting what's left is a really important factor. I like to think about this back to our glass of water is keeping our full glasses of water full. That's the most important thing we can do to keep us moving forward to address climate change. My second recommendation is restore where practical. And this certainly isn't practical everywhere, but there are places where ecosystem restoration makes a really big difference. And if we come back to our kind of natural solutions for climate change graph, we see it way down here. And if you're like me, you might have been a little disappointed by how small that green bar is. As a grassland restoration ecologist, I was really hoping that my favorite science was going to be really the one that wins the day. But I don't want to diminish that. It is an important contribution to addressing climate change. But carbon and carbon sequestration isn't the be-all and end-all of ecosystem management or of our global environmental challenges. And I want to bring your attention to these other colored bars that are next to both avoiding grassland conversion and grassland restoration. And these are the co-benefits of those actions. And this includes things like air quality, protecting biodiversity, another major threat, protecting soil in the sense of erosion, both wind and water erosion, and water quality, things like drinking water or aquatic habitats. And what these actions can provide, far above some of the other actions, are these additional benefits. So when we're thinking about the big picture and addressing the multitude of challenges our world faces today, We have to recognize that climate change is, yes, one of those, but so is declining biodiversity, and so is healthy drinking water for our communities. And when we look at protecting natural areas and restoring degraded areas where it makes sense, we can bring back all of these opportunities together. We can actually holistically address multiple goals together. So for all the overachievers out there, there's actually 5 things I want you to take home from tonight's talk. More plants in the right place with less decomposition by protecting what we have and restoring where practical. Thank you so much for your time, and I'll be happy to take questions and further this discussion.